Okay, welcome back to the last session. So as Dawood actually said, the final word is mine. so, so what we were doing yesterday, gravitational collapse problem, was that we are looking at the ADM plus Einstein Klein-Gordon system. Basically, we have a scalar field which is undergoing gravitational collapse, and then there's the self-gravity part, which is the space-time itself. And what we have done was we said, okay, since this is a canonical evolution, that is, you need to set up your initial data and have it evolve. So the covariance needs to be done away with. That is, you need to use a certain foliation or a gauge, and we split the metric. We did a 3+1 decomposition, saw how's that, and then we had the lapse shift and the spatial metric of the slicing, which is given to us. Once that is there, the Einstein equations, which in covariant form, we saw that they split up. There is the derivative of the evolution equations, the time derivative of k, which is the kij, the extrinsic curvature of the slice itself. Then you have the derivative of the gammas, which was there. And then you had two constraint equations which came out, the Hamiltonian constraint and the momentum constraint. Constraint equations need to be satisfied for all times, okay, on the surface. And so these were the four ADM equations which were there. And then we had for the Klein-Gordon field, this added the scalar field to it, and we varied the Lagrangian there and also computed what is the energy momentum for that, because that is the one which is causing the collapse, so it's a source. So that TAB or T mu nu gave us the energy density rho and the momentum flux. And the momentum, we had a projector P mu nu multiplied with it, so that gave us the projected momentum on the slice. Then what we did was we chose a particular slicing, which worked in a particular gauge. The gauge choosing which we selected was that our metric was given in terms of two quantities. So we had Ts square equals minus alpha Tr dt square plus Atr dr square. Okay. So this is what I had mentioned is what the metric which is written in the polar or radial gauge particular. The gamma RR is basically A. So and then for this set of the metric which we have, so since there are two variables A and alpha, we square. We got the equations for both alpha and A, which are basically just the momentum and the Hamiltonian constraint equations. And we saw that the two equations for alpha and A did not involve time derivatives. Right? So they were what are called elliptic equations. So you have elliptic equation, parabolic as well as hyperbolic equations. Diffusion equation is a parabolic one. This is a Poisson equation is an elliptic one, and then the wave equation is a hyperbolic one. So this was there. So we had two equations for this in A and alpha. The equation for A was essentially coming out as what was the coming from the Hamiltonian constraint. This came up from the polar the condition. Remember the time derivative of k theta theta must be 0 for all t. Okay, so that gave us that equation, which was the the polar slicing condition. And then we had the wave equation for phi t comma r, and that we split. This was a second order equation, and we split it into two equations for pi and capital phi. Two first order equations. These two, because they are coming from the wave equation, so they are hyperbolic equations. You can set the initial data and evolve it. This is what we did. Once we had the equations, then what we did was we looked at the discretization. So for discretization, we looked at finite differencing. That is, how do you transport your derivatives del r and del t on a grid, which was RT grid, the points being labeled as J delta R and delta T, where delta R and delta T I told you are the grid spacing and the temporal spacing, which of course are need to be adjusted depending upon the accuracy that you desire. Because all these derivatives under this finite differencing scheme, we used two of them. One was the central. We had j minus 1 and j plus 1, and then there was a 2 delta, there was a factor of 2 there, and then there was there was one which we had the evolution by plus and minus half. Okay. So it's also called the central cell or in cell half step computation. This I told you is needed because you had the equation for alpha and a, and these are valid for all times. And these these equations you give me phi n. And this data is given to you, and from here I can obtain phi n plus 1 j and pi n plus 1 j. However, these require data on the entire slice, single slice, and from there you get alpha n plus 1 and a n plus 1. So you give me what phi's are, and then you get your a's. Now, so much so for this thing. The equations, of course, we saw they're all horrible, so I'm not going to write them today. Okay, but what I'm going to mention is actually the discretization which we used. The scheme which we had, what is the grid which is to be used. So the grid which is usually used is what you have is you have your the axis over here, and what you usually do is you take uniform sampling. Okay, so you take the uniform sampling between 0 and 1. This is your x belongs to this thing. However, what happens is that if something is happening, you have your r which goes between 0 and some r max, which is given to you. A uniform grid will sample all the r values equally. But suppose there is something, because we are tracing a collapse. So since we are tracing a collapse, something will happen at the horizon, which needs to be identified. The program will sort of, in a way, what happens is the program actually crashes when the horizon forms. Okay, so that is when the black hole forms, and you don't know what to do when the black hole has already formed. So the code will crash. Now, in order to trace, so you look for. So this is one code which you actually crash to be successful. Okay, so what you do, we have to find what is the final location of the horizon. And when we want to find the final location of the horizon, it is actually given by where this lapse will go to 0. But it will not exactly go to 0, it will attain a very small value of 10 to the minus 5 or 3. That is up to you to set the tolerance, but it will slowly get there. So in order to resolve this thing, you need a grid which should not be uniformly sampled, but rather it should be sampled. non-uniformly, because we are not really interested in whatever is going out. I mean, rest of the school was looking at what is going out at infinity, the gravitational waves, but here we are interested in what is happening at r equal to 1, the event horizon. Okay, so we are not really interested in the regime far away, but rather near about here. So therefore, you look for what is called non-uniform sampling. So the non-uniform sampling is so how do you do that? You basically first sample uniformly and then take a nonlinear function of x, and that will give you a non-uniform sampling. So an example of that which is usually used is what is called the sin h spherical coordinates, which are defined as r is equal to a sinh x by w divided by sinh 1 over w. So you have two parameters here, capital A and w. So this capital A is like r max, because if you set x equal to 1, this is r is equal to a. So a is your what is your max? So it is the max, the boundary. You want to push this as far as possible, because what will happen is you have a scalar field, it will collapse, but it will also it will propagate outwards. When it propagates outwards, it will send reflections back, because after all you are working in not an infinite box but a finite box. So this R max is that finite thing, and you want to push it back as far as possible so that no spurious reflections arise. Okay. So this scheme sort of allows you to have it, because what you have here is then the control is given by W. It controls the sampling. So for example, you would have, now if you have X which is uniformly sampled, you will have a grid where now you will have R1 like so. So you'll have R1, R2, R3, so on, go up to R max. And for one particular value of W, say W1, you could choose another W, and that will make your sampling even more highly resolved here than far away. Okay. So it depends on, so this is your R equal to 0, and this is your R max. Okay. So this is the kind of grid. So as I was saying yesterday, this is a grid which is again, it's a fixed sampling. That is, once you have specified this function, the grid sampling is fixed. There are schemes which change your sampling. So those are the adaptive AMR procedures which are there, adaptive mesh refinement, but we'll not be considering those. So you have a fixed thing which is here. One thing I must remark, with this, you are generating more resolution at R equal to 0, less at R max, but it doesn't really care about R equal to, I mean, in the sense, you have a more resolution here than here, but actually you would desire more resolution near the horizon, but still will work with this at R equal to, I mean, with these functions. I mean, you would need more resolution actually at R equal to 1, where near the horizon is forming. So with this coordinate transformation, of course, the equations which we had derived, all of those, they can be translated into R. So that's again a simple translation. I mean, you just take the derivative dr with respect to x. So there's some let me call it some function which will come here dx, and you do the replacements everywhere in the so wherever you have del r, it will then be replaced by del x accordingly. Okay. So that's possible, and that simply samples your equations, makes your grid non-uniform. Okay. So once you have the, all the discretization schemes which we discussed in the case of del r, they are now valid over for this thing. So this is what is there. Now the question is how the evolution proceeds. So the structure of the evolution. Okay. So as I said, the two equations are Poisson. They are so how you do it is this way. So you first integrate phi to level n plus 1. Okay. Then you integrate phi to n plus 1. Okay. And then there is the Hamiltonian constraint. So you solve the Hamiltonian constraint to find A, capital A, at n plus 1. Remember, this thing was del of log A. So once you have A, you will get small a. So you compute A from capital A, and then you solve the, because see, this one is a differential equation. Okay, because there was a del r of this thing which was coming up, so that is there. Then the final step is the solve the polar slicing condition equation, which is an algebraic equation. Okay, so since that's an algebraic equation, that will give you alpha at n plus 1. Okay. And then finally, of course, you set your T nu, which you have gotten, to be n plus 1 delta t. Earlier it was just n delta t, and next one, and then go to step 1. If is t less than t final. So that's the end. So again, so these two are easy because you are given a data at n, the surface. You want to generate, given at phi at n, pi at n, you generate the n plus 1. Take those n plus 1, put them at the Hamiltonian constraint. It's a differential equation. So get capital A at all the grid points simultaneously. It's solved on sigma t n plus 1. Okay. So that will give you A all along on that, on the new surface using the new quantities, and then you solve the slicing condition algebraically. That will generate alpha, and then you repeat the process. Okay. Now in the whole thing, there are a couple of things which, so the one thing which we did not look at are the boundary conditions. So there are two boundary conditions because you have two boundaries. You have the box here, and you have the inner boundary condition and the outer boundary condition. What is happening at infinity, or what is happening at r equal to 0. So the boundary conditions, again, one can get. So if you have a spherically symmetric function let's say f of r comma t, then you know this would be equal to f minus r comma t. And in particular, this would also be true for f delta r comma t, f minus delta r comma t. Okay. So this therefore gives you the condition that f t comma delta r minus f t comma minus delta r is equal to 0, which essentially, I mean, this is just a derivative. So therefore, this essentially tells you that del r of f is equal to 0. Okay. So because we are taking delta r around r equal to 0 point. So this is the del r of this function is 0 for all times. Okay. So it's an inner boundary condition, and basically what is it doing is mapping the point on the grid onto itself. So it's basically I mean, in the sense it's a condition on the derivative. So it's a Norman boundary condition. So one can therefore put this condition on phi. So you have del r of phi at r equal to 0, del r of alpha of a. So this is that. So once you have it on, by the way, this is wait, this should be our usual phi. So once you have this thing, you can get it for capital phi and pi. Pardon? Yes. Yes. Yeah. So this is what it is, and this one essentially tells you that I mean, you know the definitions of capital phi and pi. So this just translates to capital phi t comma 0 is equal to 0, and del r of pi at r equal to 0 is 0, because pi is del r phi. So the other quantity which is I mean, so these three can be imposed. These two are just part of the matter thing, so this is fine. The only thing we need to check are these conditions, because alpha and a are also given by constraints. That is, they are not really free, but they have to also satisfy the constraint equation which are given to you. So therefore, alpha and a have to have certain I mean, they need to have obey a certain thing. So for example, I told you that the r is a radial or a areal coordinate, that is r equal to constant surface is a area 4 pi r square. Okay. So therefore, one way you could achieve this is that you take a t comma 0 to be 1, because then in this metric, this at r equal to 0, this would be 1, and you will have that. However, I'll just mention when we'll do with the outer boundary condition, what this will be an issue. So rather than equal to 1, it is better to take it as some constant, which we'll use to redefine our lapse variable, such that this is again taken care of. It will again be 1, but it will just lead to a redefinition. So we'll at the moment we can take c equal to 1. So it basically also means that there's a flatness which is guaranteed. Okay. So instead of this for a, it's better to use this. condition at r equal to 0, because these are all inner boundary conditions which is there. So, so everything works this way, and then you have the outer boundary condition. What is happening at r equal to r max? So r equal to r max, the first thing which you want to see is that there is one thing which you need to see is we are using in our finite differencing what is called the central finite differencing, that we are using j plus 1 minus j minus 1 scheme. At r equal to r max, this thing will not be there for sure. Okay, so that is one issue which you have. So therefore, first thing, how to fix this? So the fix is that for the del r's at r max, use backward differential. Okay. That is, you don't use the j plus 1, but rather use the j minus 1 and j itself. Okay. So, so you use the del r of any f and j is 3f and j minus 4 f and j minus 1 plus f and j minus 2 by 2 delta r. Okay, so this is the, and same thing is also true for the time. If you want to look at the time, there is no, for the last, I mean this thing will also be, the issue will be there also for, not just for the outer boundary, but also for t equal to 0 and t max. T equal to 0 is fine, t max, how do you calculate the time derivative? So there also you use, rather than using n plus 1 and n minus 1, because n plus 1 is not no longer there, so you just have similar to j minus 1, j minus 2, you will have n minus 1, n minus 2 divided by 2 delta n. Okay. So again, these are valid to order delta r square and delta t square. So now you need some boundary conditions on the scalar field, for example, phi boundary condition. So the boundary condition is simply that whatever field we have, we just take it that it propagates. See, what we want is asymptotically flatness. Okay, so since we want things to be asymptotically flat, whatever this field phi r comma t I have set up, it should be like a traveling wave in the far zone. It should simply go away. So therefore, it should be, it propagates to r max without being coupled to gravity at all. It's not doing anything to to gravity, because after all what we are doing is we are looking at a collapse scenario. So you take a profile of a scalar field and we want to see how it evolves. If it is going towards r equal to 0, given what the parameters are, it will either make a black hole or not make a black hole. If it makes a black hole, it will get trapped inside once the horizon form, it will get trapped inside the horizon because it is collapsed. But if it has not collapsed, if the parameter value is such that it is less than p star, so the critical value, then it will not collapse at all, but what it will do is it will go to r equal to 0 and then reflect back from r equal to 0, because r equal to 0 is a hard boundary. So it will reflect back, the space-time will stay flat because the black hole has not formed. So the space-time will settle down as flat, and this thing will have to go to r equal to infinity. So it has to travel back, not forming a black hole, so that means it does not do anything to the space-time. So it doesn't contribute or doesn't back react onto the space-time. So the solution is just, spherical wave is phi t comma r is an ingoing wave plus an outgoing wave. So you have a this over r. Okay. So this is just, it should be this way. So this you translate it to what condition it would be having at r equal to infinity or r equal to r max. That there should not be any extra radiation at the boundary. So you get the condition from here, which is del T of r phi plus del r of r phi equal to 0. This is true at r equal to r max, okay, at the outer boundary. But note, however, this thing cannot be written, I mean, this is derivative with respect to t and r. So it cannot be written separately. So you cannot separate it into capital phi and pi. So the best thing is to just leave it for phi and compute what happens for phi and pi inside the code itself. Okay. So that is what is used, and then okay, let me use this part. Okay. So you have so this is for for phi, and now next thing which you need is the boundary condition for outer boundary condition for A and alpha. Okay, what happens to those? Okay. So that again is simple because we know that they should be flat. So you need asymptotic flatness, which means that you want limit r going to r max, or which is infinity essentially. Both A goes to 1, and then for A and alpha both, they would go to 1. Okay. So you need this particular thing. So but this thing, since you want this to go to 1, this also automatically sort of you also need that del r of A at r equal to 0. We said that this is equal to 0. Okay, so both things need to be satisfied together. So essentially this is what I was saying, that these two things cannot be simultaneously satisfied. So what instead you do is that you take A alpha t comma 0. Rather than taking it to be 1, you take it to be a constant c, and then what you do is you take this c to be there, and this c could be any constant which could be present. Take the c and rescale the lapse accordingly. So take it to be a constant. The constant is decided by, when you are running the code, what would be what best guarantees that you will not generate anything spurious at the boundaries in terms of the metric. And so then this rescaling of the whole thing takes into account your asymptotically flatness, which is there. Okay. So and this thing will not change the equation. There's a reason why, because if the polar equation which we had, the polar slicing condition, that equation is actually anyway that is linear in alpha. So since it is linear in alpha, if you multiply alpha by any constant, it will not change. So the solutions will not change. So that is why you can do that. So since you have this, this sort of sets up the outer boundary conditions, the inner boundary conditions, both on the field as well as on the metric. So once you have the boundary conditions, the conditions are set. All you need to now do is give initial data and then run your problem. So initial data is, there are different ways. You could try as many initial data profiles you want. Okay. Yes.
This condition I didn't understand how this is satisfying the polar slicing condition. This, if we set it equal to C.
Yes.
How is it set? So the equation is this essentially, right?
Yes. So you write it in terms of the finite differencing which we have written. So you will see this would be alpha something minus alpha, and rest everything does not depend on alpha at all. So this would be, everything would be linear in alpha.
No, but at r equal to 0 to satisfy this, won't we require a to be equal to 1?
Why a to be equal to c? Okay, yeah. So again, the thing is, there are two requirements. One is that you have del r on a to be equal to 0, at r equal to 0, the inner boundary. Okay. So and then that is one, and then the other thing is, which I said, this is a areal coordinate, so that requires that this should be equal to 1. A at r equal to 0, because the coordinate, at the inner, wherever the what I mean is the r equal to 0 boundary, a, so we had a t comma 0 is equal to 1. So that this should be, these are areal slices, and it is flat again there also. So it should be equal to 1. However, this thing and the outer boundary condition, the outer which we want is, the outer condition which we want is that they should be going to infinity. At infinity, they should be going to 1. Okay, both together are not, you are not able to satisfy both of them together. Okay? They are not compatible with each other. Again, the way to look at it is, okay. So here is it. So you have, we sort of mention this thing. So the what? Okay. So you have the del r of alpha. So let me just write it down. So this is r equal to 0 is equal to 0. So we had del r of a at r equal to 0 equal to 0. So this was what we had done for the inner boundary condition. And then I said that for the inner boundary condition, there are two things. A also has to satisfy the Hamiltonian constraint. Since A has to satisfy the Hamiltonian constraint, there is additional, what we could do is that it has to be a radial slice. So therefore, the other condition is A t comma 0 is 1. This is what to use. So you can either use this condition or this condition as the inner condition for A. So I discarded this one, and I am using this as the inner boundary condition for A. This is the inner boundary condition for alpha. Phi and pi, of course, they are there. Now we are looking at the outer boundary condition. The outer boundary condition, since you have this thing is the one thing which is there. The other thing which you have is r goes to infinity, A also should be equal to 1. If it is equal to 1 at r equal to 0, it is 1 at r equal to infinity, it will not evolve. Again, the reason is you simply have, you have it equal to 1 here, you have it equal to 1 here, it will be 1 everywhere. Okay. So what you do is, rather than setting it equal to 1, you set it equal to a certain, so rather than using this here, this is fine. You have to take this to be the outer boundary condition. The problem is with the inner one. Rather than taking this equal to 1, you take it to be C. But this C is something which is changing. So you decide this C on the basis of your code. So for example, C here is given by, you could select, so C is, so this is one option. So you take for every, so you have 0 j less than capital J. So let us say you have total number of points in space are j, capital J. So for each one of them, you have to select this thing. So you select the minimum of a particular quantity, which is a j n plus 1 by alpha j n plus n. So if you choose, for example, this constant, for every grid point, a different constant would be there. You run it for j equal to 1, 2, 3 up to capital J. Use this constant instead. That will set the things for you. Okay, so this is one choice. There are different choices of C which are available to you, okay, which is something which you can use. And then this and this one will be consistent. Setting this equal to 1 will alone will not be. But the main issue is, if you set it equal to C, does your equation change? The del t of k theta theta equal to 0, does it change? It does not, because it is linear or homogeneous in alpha. So you can rescale it. Rescale it and it will not change at all. Okay. So essentially what the whole thing actually does is this, that whatever choice you make, a constant choice, it sets a at t comma r max equal to alpha of t comma r max. So they both become equal. Now you just at maximum at the outer boundary condition, they both are equal. So if alpha is going to 1, a will automatically go to 1. So both are guaranteed together. So the initial data. So what initial data you use? There are different profiles which are possible. So one profile which is used is phi 0 comma r is eta exponential minus r naught square by delta square. So this is one profile, and del t of phi 0 comma r is 0. This is one such initial data which was used by Choptic. So you see there are three parameters here. So you have r naught, you have delta, and then you have eta. So eta tells you, r naught is just again wherever it is centered, delta is the width, and eta tells you the amplitude. Okay, so when I had mentioned you have S parameters, so you have all three of them. So usually delta and eta are kept fixed, r naught and delta are kept fixed. And eta is the one which we will vary. So you can choose various, so the runs are made by changing, so keeping these fixed, but by changing eta. So there is some eta star which is there. For values less than eta star, you will form a black hole. You will not form a black hole. For values which are greater than eta star, you will form a black hole. And how do you decide this eta star? Again, this is done empirically. Okay. There is no other way to see whether what is the value here. So you set it empirically. So for eta less than eta star, you will not form a black hole. The wave will simply come in and disperse away. It will leave you a flat space-time. But when you have eta greater than eta star, that is, you have a certain amplitude here, larger, it will form a black hole. Now the profiles which usually are, so you set r naught equal to 0 and delta equal to 1, for example. This is one such initial data. So that will just be, this will become eta exponential minus r square, and this is just phi 0 comma r, and then this means your capital phi 0 comma r is essentially minus 2r eta exponential minus r square, and pi 0r is 0. Okay. So this is one example which is there of a profile. So how does it look like? Essentially it looks like So what you have at t equal to 0 is something like this. So this is 0 and this will have some phi max. So this is r equal to 0 and up to r max. This will be your profile. It should be there. Now there is one more quantity which we usually want, which we look at is essentially whether or not the black hole forms is also given by something called the mass aspect function, which is essentially coming from A. So you take your A square and so which is over here with dr square, and you equate it directly to your, if it was a Schwarzschild like solution, so 2m by r, where m is a function of t and r. So this therefore defines for you m tr as a function of a square. So there are 4 quantities which we are evolving. So we are giving a initial data of phi and pi, and then so we have where is it? So we give phi and pi, use the constraints to get A and alpha. From A you get capital A. Substitute that in the equations. So then you have the full data which is available to you is phi, pi, A and alpha. Okay, that is being something which is being evolved for these parameter values. So one can look at the profiles, what happens to them. And now depending upon, as I said, depending upon the amplitude, the function which we are using, the eta, you would be either in the black hole formation scheme or in the scheme where there are no black hole forms. So that these people, they define it as weak or strong regions. Weak is the one where there is no black hole formation, and strong is where you have black hole formation. So what does, how do you track the formation of a black hole? Well, you look at laps. Okay. So you have laps initially is given to you something like, it goes like this. Okay. You track what is happening to laps as time progresses. So this is t equal to 0. All of them are t equal to 0. Let us look at what will happen in the weak regime. Of course, this is better done when you actually do the run the code and see what happens. But sort of we can still get the analysis here. If you do not have any black hole forming, we saw that this phi would be like a spherical wave which will just travel out. So what you will see is that essentially this phi, it will there will be a pulse which will travel further and further outward. So this is one, this would happen. The next thing would be until it has completely traveled out of the system. So you had a profile you start with in a box. So this is also there in a box. And when the time runs, this would be a pulse because it comes to r equal to 0 and then goes back. So it will settle down, and the space time, it will, there will be no traces which will be left here. m would be 0, of course, and the space-time would be left flat. So what will happen to alpha is that alpha will also, it has a profile like this. Soon this will evolve, so it will go into something like this, this, and then settle to a constant value. It will freeze out. It will freeze out close to 1 because you are left with flat space-time. Okay? So this is the case where there is no black hole formation taking place. Of course, you can also compute this mass function here, and mass function will be 0 at the end of your simulation, because you will start with something. There is a scale, there's a scalar field which is there. The profile is there. It will have a certain mass, and soon as it travels out, it just simply goes away, goes out of the boundary, and there's nothing left there. The mass will also go to 0. Okay. However, when the black hole forms, then the final value of your mass, so this mass which you have here, this final value will go to m ADM. Okay. The ADM mass which is there, and that again you can see. So what happens if you want, when you're in a strong regime? In a strong regime, rather than this, what will happen to phi is, so you have started with the profile like this. It will, since it's collapsing and the horizon is forming, it will get trapped within a particular region. So this would be r equal to 1. The horizon will form here at r equal to 1. It will get frozen thereafter. It will stay like that. How do you see the formation of a horizon? You see the formation of horizon by looking at alpha. Because you know the lapse vanishes when the horizon forms. So lapse alpha has to vanish. And the way alpha vanishes is it starts from something, earlier you had given it, let's say, a non-zero value. So this is, it starts with a non-zero value, has a profile like that. Subsequently, it will come lower and lower, and it will hit r equal to 0. The level alpha equal to 0. So when it hits alpha equal to 0, and the place where it hits, that comes out to be the location of the event horizon, the horizon is formed. So all throughout you can calculate various quantities. For example, I mean, this is a dynamical case. The event horizon, it's not really an event horizon which forms, but rather a dynamical thing which is happening. So the final, for example, the final alpha will look something like this. Okay, so it is exactly 0 here. What it tells you is that alpha was lapse, right? It is telling you how time is changing between one hypersurface to another. Okay. If alpha has gone to 0, that tells you there is no time lapse which is happening. And that is exactly also what is happening here for the scalar field which is inside, collapsed inside, there is no time lapse. So it is frozen. So for the scalar field, the proper time lapse is 0 when the horizon is formed. Okay. So in this way, you are simply sort of tracking what is happening to this thing. And now for the for mass, you can see that if you're computing the mass function t comma r with r, you will see that it will have a profile again. So this is r equal to 0, 1, so on. So the profile is something like this. Okay. This will be your same as your, so the mass which you have outside, so the value would be same as your ADM mass for the initial data which you have given. That is because that's the only scalar field which you have. So if you compute the ADM mass for the initial data, this will match that in the case of formation of a black hole. So how do you decide what? So what parameters basically decided is all decided by eta. So given you have eta less than eta less than eta star, there would be no black hole. Eta greater than eta star, there is a black hole formation taking place. But then the question is what happens when eta is close to eta star or something. And then again you can find evolve the system and find this m. And that is where I was telling the scaling law takes place. When you take your initial data and you find your m, it goes as eta minus eta star to the power gamma. Okay. So the mass of black hole which is formed in that particular case is follows a critical law. Now what happens, so the codes are usually get very unstable during that time. So there is a formulation which, the ADM formulation is slightly a sort of issue which is there. People use what is called the BSSN formalism. Again, what you, I'm not going to details of the BSSN formalism, but what you do is essentially in the BSSN case, we have two quantities gamma ij and k ij. Okay, that is what we are looking from the perspective of the evolution of the gravitational degrees of freedom. Rather than looking at these, you look at what are called conformally transformed. So you write gamma ij tilde as some, let us say, w square gamma ij. Okay, so where this is a conformally free part of gamma. Similarly, you take k ij and work with k, its trace, and some aij, which is the trace free part of extrinsic curvature. And when you work with these two quantities, and additionally, in order to have a numerical instability, you also introduce another auxiliary field, let us say gamma alpha, and that takes care of the numerical, it sort of absorbs the instabilities, which allows you a much stable evolution. Okay, so that's one thing which is there done in the BSSN formalism. More about this can be found in a book by Shibata. It's 100 years of relativity or something like that. And the title, I mean, the series is 100 years of relativity, and the title is numerical relativity. Okay. So regarding what happens to, in the case of a critical, in the critical parameter, what happens to these values? As I said, the profiles, you start with these profiles, the again initial profiles are the same, but the end results alpha and a, they develop a self-similar structure. That is, you will see the profiles which will develop have a fractal-like structure built into them. So that's where the critical phenomena takes place. So essentially, you have this thing which is there. This is what I sort of wanted to cover. I will strongly advise that you download and work with this code. It's just it's there on GitHub. You can clone the repository, and it runs. I mean, it's a modest. It runs on the machines of now. It's not a problem there. So you should definitely check it out. Again, this is once again the name of the code is. Spherical collapse 1D by Leonardo Wernick. Okay, so you should definitely check this out. So, I mean, there are great many things which are still open in numerical relativity, particularly with the gravitational collapse. There are interesting possibilities. We took a real scalar field here. An interesting other possibility which people have considered is that you take a complex scalar field, and then that will have a charge built in. So that's where you form black holes with a charge. So that Q charge will also come in. Then there's something which we have also been looking at is these are all classical collapse scenarios. You have a classical field which is undergoing collapse. What really happens, suppose if you had a quantum field to begin with. But that's a whole different problem, because you just don't have to specify phi alone, but you also have to specify the state in which it is there, because it's a quantum field. And then since you have to specify the state as well, so every time you have to compute these expectation values. So it's a little more challenging problem to look at. Okay, so I'll stop here. That would be all from my side. Wish you all the best in numerical relativity.